I'm bit kerja.
But yeah, do you give me consent on recording the session and uploading
Yeah,
on
yeah,
YouTube?
yeah,
Okay.
yeah. No worries, no worries.
All right. Good to know. Good to know. Okay, okay, okay. Because I don't want to be in any kind of lawsuit in the future.
Oh no, no, no worries, no worries.
Okay, okay, okay. Good to know. All
Okay.
right. I'm
Uh,
safe now.
so about question 18. Yeah, 18. I think it's negative 2 over n multiplied by square root of n, I think.
All right.
Yeah, I kind of confused. I mean, I tried doing the integral test, but then
Okay.
see, I got confused whether should I keep on going or do I like, because when I look at the answer scheme, I got it wrong because they used P series. So I macam
But
got confused.
but does the scheme answer state it converges, right? I believe it converges, right?
Jit, jit, jit. Ah, yeah, yeah, it converges.
All
Mm-mm.
right. So I believe like this section, they want us to test whether or not we could apply integral test.
Mm-hmm.
But basically, right, if you see this series, you don't need to show
Yeah.
that. Means that you know P series, right? You know what are the
Okay.
conditions for the
Okay.
P value
Mm-hmm.
larger, less than one. So
Mm-hmm.
for now, the question, the question's objective is to see whether or not you can apply integral test, which is like
Mm-hmm.
question 18 now.
Mm-hmm.
But yeah, that's basically the idea lah. But I believe the scheme answer uses P series, right? They just use P series.
Yeah, but initially I just go on with the integral. Just like basically what I get is like integral of 1 over x 3 over 2, and then I just integrate it and then went on with it. So macam, but then the scheme said, oh, you can stop there and then use, then because since it's in the form of P series already, because you
Okay,
have
yeah,
like x to the power of, we have 1 over x to the power of something, so it's already like a P series punya form. So I guess like my question is like when to know, when to know, you know, when to use it. Like when to stop and say okay, this looks like P series, or when to continue on with the integral test gitu lah.
I see.
Mm.
So I
But
believe P series.
yeah.
If you remember, what are the
Mm-hmm.
conditions for P? Whether or not it's
Mm-hmm.
larger than one, less than equal to
Yeah.
one, or
Mm-hmm.
even equal to one. Then what are the
Mm-hmm.
outcomes whenever you use a series? Sorry,
Mm-hmm.
less than equal to one is the same as equal to one, so less than equal to one. So what are the
Yeah.
outcomes? Like larger than one, what does it imply to? Less than equal to one, what does it imply to the series? Um, I mean that in this case,
Mm-hmm.
this series is simple enough to use P series directly without even use
Yeah.
integral test.
Okay, so you macam, so take out the negative 2 and then
Yep.
n times square root of n, you already see that it's n to the power of 3 over 2, macam tu?
Oh yeah, yeah.
Okay.
So
Oh, I
yeah,
see.
the way we want to state our answer is that okay, we have this right. This is equal
Mm-hmm.
to negative two times the series,
Mm-hmm.
and then the way I wrote my answer right is in a
Okay.
sentence like since
Sentence. Mm-hmm.
it's a P series where P is equal to 3 over 2, where that is larger than 1, the series, the series n is equal to 1 to infinity, 1 over n for 3 over 2 converges, and therefore negative 2 over n 3 over 2 converges. Because it's a fact that it doesn't matter whether this series converge or diverge, any multiple in front of it, when it multiplies a converging or diverging series, there is also a diverging series or a converging series based on what you know about the series lah, in a way. Okay. So yeah,
Understand?
the way you want to do it is that you have not state this is not a P series yet. You have to bring out the
Mm-hmm.
constant up front. Then you could
Mm-hmm.
say this is a P series. Then you could give a sentence on um why are you saying it's converging? And then you conclude that the multiple of -2 also converges, just like that.
Uh-huh. Okay, I see. So, like, basically, for this question, easy to use. It's easy to see lah. So no need to continue with the integral lah. Macam no need
Oh
to
yeah, yeah,
find.
yeah.
Okay. So if we cannot get in the form of P series, then that's when we can try lah the integral. Is it? Betul?
For me, integral test is the last resort because integral test you
Okay.
have to know how to integrate. That's the
Ah,
fundamental part about the test. You have to know
I
how to
see.
integrate it. If you can't integrate,
Mm.
then it's useless. And that's the downside of the test. And if the integral is tough, then
Then I
it's
have to use
either
other
you
methods.
yeah, much more efficient.
Mm.
This course is
Okay.
all about being efficient in a way.
Yeah,
Mm.
okay, I agree. Agree.
It's like
Okay.
one of the series I think is this series for question 13. Question 13, we have this series. You could use integral test. You know how to integrate exponents, right? Yes, you can integrate this very directly, but it is also a geometric series. If you could like make it in this form, then you could say this is your common ratio. Then we know, generally a common ratio, if it's less than one, it converges, right? So
Mhm.
yeah, so this is much more simpler lah, because you recognize it's a geometric series. Therefore, you don't need the integral
Mm,
test to solve
I
it directly. Yeah.
see.
Yep.
Okay, okay. All right. Understand.
All right. So
The next
yeah, yeah.
one,
Go ahead.
uh, 24. I
All right.
think it's like something like 5 to the power of n over 4 to
Okay.
the power of n plus 3.
All right. Mm.
So I'm not sure about this one because this one I don't think you can integrate. I don't think so. Definitely.
Yeah,
I
you
think
can't you can't
because
integrate.
yeah.
I mean, you can, but I think it's a hard
uh,
one.
no,
It's
yeah, yeah, definitely it's not.
yeah, yeah.
No. So like yeah, like I'm not sure how to go about this one, like because it's not you can't even change it to a P series, right? It doesn't look
Yes,
like P,
it's
doesn't
not a
can't
P
even use
series. Yeah.
integral. So like how do I go about this part?
Mm.
Yeah.
So there are a few ways,
Mm-hmm.
a few tests you can do. One is whenever I tell anyone who has some difficulty, some having a hard time to solve series, I usually told them to, okay, the first thing with first is by applying the divergence test or n-term test. That's the most, that's the simplest test. All you have to do is just find the limit for the given sequence. And if it's not equal to zero, then it diverges from there. So, but now, how can we apply n-term test? All right, first things first. Okay, we write down our series. So, and what we could learn from here is n-term test. Now, what does this? Oh, sorry. What does this tells us? Let's say you have series. All right, you have a series here. So, what happens when you take the limit and n approaches to infinity for a subscript n? If it's not equal to zero, then it diverges. But what happens if it equals to zero? The test fails. That's basically it. If it's equal to zero, then you have to use another test to determine whether it converges or diverges. Because there are a few series that it doesn't apply, that doesn't satisfies the test, like harmonic series. Well, harmonic series, the sequence of the harmonic series converges, approaching zero, but then the series diverges. So when you apply the n-term test, you can see that it approaches zero, but it doesn't imply that the series converges. It could be diverging. So how do you apply for this series? Now, writing this first, taking the limit for 5 to the power of n over 4 to the power of n plus 3. Now, Doctor did mention on how to solve it is that you divide all the terms, the highest value on our denominator, the highest power, the highest value of term. Anyway, so we see the denominator, the highest value will be 4 to the power of n. So by dividing all terms with 4 to the power of n, we are left with this. As you can see, this and this, right?
Uh-huh. Mm-hmm.
This approaching 0 because the denominator becomes larger, so the whole term approaches 0 in a way. And we know that the numerator here approaches to infinity because it's a well, I could say that it's larger than 1, so
Mm,
it approaches to infinity as it becomes larger. So the whole thing, this whole term, approaches infinity. So this is not equal to 0. So from here we could see that it diverges. But
mm,
how about other tests? Maybe direct comparison test 9.4, even though we haven't reached to 9.4, but this series we could also use direct comparison test. Now, how about direct comparison test? What does it tell us mostly? So direct comparison test, we have series like A and B. Both of the series have positive terms, and there are three situations, I believe. One is which that when you, yeah, sorry, two. The three situations are for limit comparison test. But here for direct comparison test, let's see. So let's say we have this A, B for all n such that larger than n, some number n. So this inequality only works if B it converges. If B converges, then A converges.
oh, so meaning we have to know the series B series lah, whether it converge. We have to know it first lah.
Yep.
The, the
The B
uh
is for the known series that we know
mm,
initially that to compare with. Same goes for this
mm,
inequality. For all n larger or equal to n, so B has to diverge. If B diverges, then A also diverges. Okay, so
uh-huh.
let's see. But it's possible this test fails as well. So you could use limit comparison test and you can see where that goes from there. So let's try. So this series, I believe that we can compare with, let me imagine it first. So um, for, yeah, it's larger. No, okay, yeah. So we have, we could compare with 5 to the power of n over 4 to the power of n. And as you can see here, this is a geometric series. But the question is, diverges or converges? We know that the common ratio is 5 over 4, and 5 over 4 is larger than 1. So it diverges.
Mm-hmm.
So
Uh-huh.
let's build the inequality. So the way we want to build the inequality is that first we wrote down both series side by side, like the following. And the reason why this works is because that the terms are always positive. Then the inequality sign doesn't change no matter what value of n, because n is a natural domain, 1 up until infinity. So the inequality, no matter what happens, you multiply both sides, you take away both sides, it doesn't change. Unless if you multiply both sides with a negative value, then obviously the sign changes from maybe less than equal to larger equal to, and so on. But here, we could do whatever you want. You could apply the basic arithmetic rules to it, and nothing
Mm-hmm.
will change. The inequality sign will unchanged. So this middle spot here will be the sign, but we will not write it down. Okay, we will try to compare both sides and see which side is bigger. Then we could write down the signs. Okay, so from
Oh,
here, I know here I could expand the exponent, this, and I could see that I could multiply both sides with their respective denominators and numerators, and basically this could be cancelled out. We are left with 4 to the power of n plus 3, 4 to the power of n. As you can see, this sign is larger, will always be larger. Our series starts from 1, right? So this satisfies for all n larger than or equal to 1 because this case is equal, and this plus 3. So no matter what n value, it will always be larger than the right hand side. So we can conclude that it will be larger equal to for all n larger equal to 1. So what does this mean?
Mhm.
This means this is always larger than this, I believe.
Mhm.
Okay.
Mhm. Mhm.
But the problem is when we build the inequality, what happens? We have 5 to the power of n over 4 to the power of n plus 3 less than or equal to 5 over 4 to the power of n. But the question is, does this work? Does this work for the direct comparison test as we go back here? It says that B is our known series, which is, well, 5 over n, 5 over 4 to the power of n, and it has to converge. But here we know it diverges, and the inequality is in this form, which is our first inequality based on the test here. Unfortunately, our known series doesn't converge, it diverges. So, well, it fails. We can't do anything about it. But doesn't mean it does it fail for limit comparison test though? Let's check it out. Limit comparison test. Now, limit comparison test, what does it tell us? We have three cases. Let's say the series A, series B are positive terms. Okay. And what happens when we take the limit when n approaches to infinity? So the first one will be A over B. So from initially, B will always be our known series and A will be the test series. So I will not be changing the variables so that it will not be too confusing on the long run. So just to remind ourselves that B is our known series and A is our test series. So here we have A over B, where A is our test series and B is our known series. And if the evaluate limit is C, where C is larger than 0, then we could say that if B diverges or converges, then A maybe also diverges or converges. It means that, let's say B diverges, then A diverges. So let's say B converges, then A converges as well. This only implies for when the resulting limit is something larger than 0, I believe. Okay? But
Mhm.
there's a second case where the same limit, but the the limit is equal to 0. Now this only works if B converges. So if B converges, then A also converges. Does it diverge? What happens if B diverges, but our resulting limit is 0? Then obviously the test fails. So we have our third situation where the limit n approaches to infinity, where A over B is equal to infinity. Now this only works if B diverges. So if B diverges, then A diverges. So that's basically it. Now let's try and apply the limit. So limit n approaches to infinity. So we know that A is our known series, test series, which is 5 to the power of n over 4 to the power of n plus 3. And then our test series is what 5 over 4, on which we have to flip it since it's dividing by it. And it will be 4 over 5 to the power of n. Okay, seems promising enough. So here we know the limit n approaches to infinity, where we have 5 over 4, okay, 20 to the power of n over 20 to the power of n plus 3 times 5 to the power of n. So we know that this is our largest term, lah. Okay, so we divide everything with 20 to the power of n. So we have limit n approaches to infinity, 1 divided by 1 plus 3, 5 over 20 to the power of n. Okay, and this resulting limit Well, since this approaching to zero, if I'm mistaken, yeah, it approaching to zero, then this whole thing will be zero lah. So you are left with one, and one is larger than zero. So, well, the test says that if it's larger than zero, then this will be our conclusion, where we know
Mhm.
that B diverges, then A diverges. So yeah, limit comparison test works. So this series diverges. So now we have two tests that satisfies one. The first one is which the anthem test. Where is it? Here it is. Anthem test. Sorry, on this one, anthem test. It states that it diverges. Okay, but direct
Mm.
comparison test fails. But limit comparison test satisfies the conditions for the test, and it shows that the series diverges. So yeah, there are two ways to show lah.
Ah. Uh-huh. Uh-huh. Wait,
Yeah.
can we go back to why the DCT doesn't work? Because I
Here you go. Yeah, here.
okay. Um, it says, oh, it's greater, but then it doesn't fit with the condition, eh? Kejap. I
Yes.
think. Oh,
Yeah, here
okay.
it has to converge, but in this case, it
Mm-hmm.
diverges, so it doesn't satisfy the conditions for the direct comparison test.
Oh, okay, okay. Uh-huh. I guess, yeah, I was about to ask about 9.4 because the question, like the one thing that I struggle is when to use these, like when to use DCT, when to use LCT, or do I have to like yeah, I guess like when should I use the like DCT lah and LCT macam tu lah.
I
Um
see. Okay, okay.
yeah, like uh any like any rule of thumb that you would suggest or or how like yeah.
For me, it's hard to say that how what's
Mhm,
the strategy on knowing
mhm,
that which test is suitable. Because
mhm,
sometimes
mhm,
there are some series where we see that we could apply root test because the numerator and the denominator both have powers of n. Therefore, the root test has to cancel out and it has to give the conclusion for the test. But unfortunately, we know that the root test, if it's equal to one, the limit is equal to one, then the test fails. We can't say anything about it. It doesn't converge or diverge. You can't make any conclusion from the test. So all I'm saying is that the only way to really know whether it converge or diverge is from experience. You have to do the labor, which means that you have to do the exercises. Most of them, yeah. If you can, maybe you could try
mhm,
some odd number questions as well. Even though the
mhm,
tutorial they suggest that we do even numbered questions, but
mhm,
it doesn't hurt to do a few odd questions just to see how far we understood on on applying those tests given.
understood, understood. Yeah, that's true, that's true. Okay, okay. So number so 24 there's like two ways to do it lah. Okay. If
Yes,
we really think of that. Okay, okay. But but I think I it's diverge, right? I mean
yeah, I
I
believe it diverges. Yeah, yeah.
that's what I did for 24 is that macam since I cannot use integral, I did macam I think how you did it was anthem test, right? Where you find the limit of the series. Is it? Nak
The
kata.
sequence, yeah, a subscript n.
Right.
Yep.
Sequence. Yeah lah. Like, okay, okay. So I did that, and then but I didn't know that you can also do well, limit LCT juga. Okay. Right. That's new to me. Yeah. Um. And then okay. The other one that I want to ask, which I had issue with, is number 20. Sorry, 22. I already jumped to 24. Sorry, can we go to 22?
Okay, okay.
Yeah, I did not see that. I lupa. Yeah, 22 is I think ln n to the ln n over and square root n. I think that's similar. Mm-hmm.
I see. Yeah, yeah, yeah. Log n over square of n. Yeah.
Yeah, but I tried. Okay, again, I tried using integral test, then
Mm,
I got stuck. Yeah, I think I
mm,
got stuck because I tried using substitution, but then
mm, mm.
wait, is it right? I think I use substitution to get rid of the ln x and ln x plus square root x and
Oh,
mm,
you apply the integral test, is it?
yeah, yeah, but it took me so long. Like it's confusing. Yeah, I kind of got stuck there lah. So yeah,
All right.
then but yeah, integral. Yeah, yes, I use integral test, but I'm not sure whether it's correct to start. Can I? Yeah,
I believe
is there like
that.
another?
Um.
Mhm.
Oh yeah, yeah. I think there's a better one on solving without
Oh,
using integral
okay,
test.
okay.
So the way we want to approach this is that because this technique, it's not technique, it's a fact that doctor mentioned in class on this kind of series on how to show whether or not it converge or diverge. Is that maybe let me just recall a bit. I believe um yeah. So we have this thing. I think it's from my notes. Let me. Do I have it? Did I bring it? Oh, I didn't bring it. Ah, damn. But if I recall, on some series, say we have this series ln n over n to power c weight p, right? Now, the way we because this series we could use, I believe, limit comparison or direct comparison. But now the question is, which series is suitable to apply it, right? Which series is suitable?
Yep.
Mm,
Yeah, definitely not. I mean, it's not PC. I cannot.
yeah,
Cannot.
it's not a PC. Yeah, it is a P series.
I mean, if you can get rid of the long end lah, that would be really nice. So,
But does
but
it have to be like that? It means that
uh-huh.
I think. Oh wait, can we do that? Wait, P. I need to recall a bit. Less than less than one. It has to be larger. Oh yeah, yeah, yeah.
I
I don't
mean,
think we
can you
can
use the comparison test for this? Because you
limit.
can.
Oh yeah, I believe we can. Huh? Satu je kot. Sekejap, let me open my tutorial book. I think I
No
did this
worries.
before. Anyway, sequence. This is 10.3, right? 22. Oh,
Yep, yep.
oh, yeah. Okay. I just remembered that we can't use this fact is because that the condition to it is if you want to
Mhm,
compare is some p
mhm,
series 1 over nc. This will be c. This will be p. It has to be 1 less than equal to p, where p is less than equal to c. But the problem is this value is 1 over 2 to the power of 1 over 2, right? So it doesn't
mhm.
satisfy this. Wait, yeah, it doesn't satisfy. Yeah, it doesn't satisfy.
Mm,
So this thing we can't apply lah. We can't do this one.
I see.
However, we can use the integral test. But have you applied the integral test lah? Do you?
Yeah, but I was like confused on the. I think I got confused with how to integrate like ln. Is it ln? Yeah, ln n over. Eh,
Square root of
I
n.
changed it to x lah. Ln x over square root x lah. Gitu lah.
I see, I
But
see.
yeah, I think.
Okay. But yeah, so I just remember we could use integral test. So first things
Mm,
first, let us write down the conditions to apply the integral test. So there are three conditions. One is which the function has to be positive
mm-hmm.
on the
Oh yeah.
domain.
True.
The second one is that it's a decreasing function. And the third condition, it has to be continuous. Now, the domain will be from 2 up until infinity. So we would like to define our function in that domain. So by defining it, will be f of x is equal to ln of x over square root of x, where x is larger than or equal to 2. Okay?
So you have to write it like that first lah before integrating something.
Ah, yes, yes. But now
Okay,
the
okay.
question is, does it satisfy the conditions before we can apply the test? So we know it is positive. Is it a decreasing function? Who knows? But we had to show that it
Mm,
is a decreasing function. Is it continuous? Yes. Because
mhm,
the only value of x that it doesn't satisfy this is that from negative infinity up until 0. This is the
okay.
domain that it doesn't
Mhm,
satisfy this because obviously
mhm,
there can't be negative values for the square root, also for the ln. But if the ln has an absolute value, then that's a different story.
mhm,
But in this case, there's infinite absolute value. And also, the square root only takes positive values. So this domain is unsuitable. But in this
mhm,
domain, it is continuous for all x in that domain. Therefore, it is continuous. But how do we show it is a decreasing function? There are two ways to show it is a decreasing function. One is which that you use the inequality, like you know the u subscript n and u subscript n plus 1. Now, this is the current term. This is the next consecutive term. So if you could show that this is always larger than this for all n, then it is decreasing. But for long functions divided by some function, it's going to be tough to show it is a decreasing function. So another way to show is that you find the first derivative, because the first derivative, it tells us the slope of the function. So if it's less than 0, which it means that it's a negative slope, which means that it goes downwards, decreasing, right? Or slope. So, but you have to show it, obviously. So we know that this is a, well, it's not an algebraic function, it's a transcendental, right? Because the denominator is a transcendental function. But in this case, you could apply the, oh, sorry, it's not, it's a quotient rule. Now you have to remind yourself how to apply the quotient rule, which is vu prime plus uv prime over v squared. So uv prime, sorry, vu prime minus uv prime. So our function of v will be square root of x, and u prime is just the derivative of ln x, so it'll be 1 over x. Then minus with uv prime. So u is ln of x, and v prime is the derivative of the square root of x, will be 1 over 2 square root of x, divided by square root of x square. But you could eliminate the square root, and the square will be x only. Okay. You don't need the absolute value
okay.
because here the domain will always be positive, so you could ignore the absolute value. You don't need to put it. Anyway, to solve this, okay, first things first, you have to simplify. Okay, and now just combine these two. So it will be, if I'm mistaken, it will be 2 minus ln x over square root of x, if I'm not mistaken. Yeah, that should be it. Okay, all right. So now, 1 over square root of x. Okay, all right. So the question is, well, when x is equal to 2, the slope is positive. Am I right? If I'm not mistaken, the slope should be positive.
Yeah, betul. True.
And
Mhm.
when x is e, the slope is still positive. So when does it start to be negative? We don't care about these values initially, because we want to see what happens when this graph goes to infinity. So at some point, ln of x will be larger than 2. So let's see, because in order to make this as 0, some x value has to be satisfying the ln function, and it will be equal to 2 lah. So let's find that first. So it will be e to the power 2 lah. So from e to the power of 2 towards infinity, the function will be a decreasing function, right? And the reason why this condition holds is because that we want to see what happens when it approaches to infinity. Is it always decreasing, or are there some x values where it increases all of a sudden? Therefore, it does satisfy the condition. But here, from x is equal to e to the power of 2 up until infinity, the function decreases, right? Okay,
Okay, I understand. Understand.
so you could say here that it's less than 0 for all x larger than or equal to e to the power of 2. So it is a decreasing function, right? So
Mm,
now it is a decreasing function. So what happens next? Well, integrate. So you have the function of f ln x over square root of x. Now the question is, how are you going to integrate this? Well, we have various techniques. Integrate by partial fractions, trig sub. But in this situation, the most suitable technique is by using integration by part. So integration by part is just basically you applying a formula, which is uv is equal to uv minus the integral of v du. I will not be showing the proof how I derived this, but this is the idea.
oh, mhm.
Now the question is, which one is suitable to be our variable dv and which one is suitable to be our variable u? Now, as Dr. says, you have to try and error, but in this case, the most best way to present your variable is dv is when it's equal to, wait, before this, I have to write the integral. So do up until infinity for ln x over square root of x dx. Okay, now dv, I think the most suitable variable will be 1 over square root of x. And for you, it will be ln of x because when you apply, well, for dv, you have to integrate to v, so it will be 2 square root of x. And you will you integrate in respect of x, it will be 1 over x. Now, the reason why I say it's suitable is because that, well, this combination, we can integrate easily without having to handle or solving another function which doesn't relate to the function of x, the square root of x. Okay, and
Right.
here by applying the formula, you are left with 2 square root of x ln x. Okay, then minus with the integral of 2 over square root of x. If I'm mistaken, yeah, dx.
Yeah.
Okay. Now, integrate as usual. So it'll be 2 square root of x ln x minus 4 square root of x plus c. Now, this is your indefinite integral, and all you have to do is just plug it into your definite integrals. Let me move around to give some space. And let's try and solve this. So we have our definite integral. Well, it's an improper integral type 1 from 2 to infinity ln x over square root of x dx. Now, the resultant integral, well, before you have to write down the resultant integral, you have to follow the working. The working has to be correct. So you have to find the limit, where the limit b approaches to infinity, on which 2, the lower boundary, and the upper boundary will be b, for ln x over square root of x dx. And you have to solve the limit. Limit b approaches to infinity will be 2 square root of x ln x minus 4 square root of x b2. And just replace the upper lower bound. So you will have the following: 2 square b ln b minus 4 square root of b, and then minus 2 square root of 2 ln 2 plus 4 square root of 2. Now, basically, I believe you can factor this out. It will be ln b infinity square root of b, well, 2 square root of b ln b minus 2. And then we have, well, this is their own limit, and then we have negative 2 square root of 2 ln 2 plus, what is this? Oh, 4 square root of 2. Now this term, long b will be, well, long b will approaching to infinity, and when infinity minus 2, it will still be infinity, and 2 square b will be infinity, so infinity times infinity will still be infinity. It will be a larger number, and a much
Mm,
larger number with this term, it will still be infinity. So in
Okay.
proper integrals, if the resulting integral is equal to infinity, then it means it diverges.
Mm,
Therefore, from the integral test, the series diverges.
I see.
Sorry, this is the x, and this it's not x, it's long. All right, diverges.
Mm. Uh-huh. Okay, I think I didn't use integrate by parts. I think that's why I got like lost. But okay, now I understand now. Okay, okay. Uh-huh. So like so I have like in order to use the integral test, it has to comply lah with the three that you mentioned lah, continuous, positive, and decreasing.
Yep,
Decreasing
yeah, yep.
function, you have to use the derivatives lah. Is it macam uh
Well, yeah, derivative,
mm,
but if it's an
uh-huh.
algebraic function,
Okay.
then you could just use the inequality. You have to build the inequality. Like you have to show that the
Oh,
consecutive term is lesser than the current term, which is
I
yeah.
see. Okay. Sorry if it sounds silly, but is it like when you say algebraic and then use inequality, is it almost the same? I mean, is it like if I want to like list out all the like some part like the sequence, like some maybe the first few terms and see that it is decreasing, is that one way to check? Or is that like not really the best way to find out whether
I
that's
mean,
decreasing or not?
if you want to like convince yourself that it is decreasing, then you could compute a few terms. But then
Oh,
at the
okay.
end of the day, you have to show that it satisfies for all values of x in the domain,
I see.
and you have to
Okay.
show it algebraically. Yeah.
Mm.
So let's say right,
Um,
you
mhm.
have 1/x, okay, and then you want to show that let's say we have the term t subscript n will always be larger than equal to t subscript n plus 1. So the way we want to show is that by writing down 1 over x plus 1, no, sorry, n, n plus 1. And as you can see, since n is a natural number, then there's no problem of oh, the canceling both denominators, the inequality will not change. So we have n plus 1 and n. And then n can be subscribed both sides. We have 1, 0. Now from here,
Mhm.
it's larger than equal to 0. Oh, it does satisfy. So this shows that t subscript n it will always be larger than t subscript n plus 1 for all n in the domain. Let's say, yeah.
Oh, I see. So this is the way to go if we're dealing with algebraic, and I mean we want to do it by building inequalities lah.
Yeah, it's an easier
Right.
way lah. Yeah,
I
if
see.
you could
Because
like
this is kind of new to me in a way, so I learned something. I
yeah,
see.
I also
Okay.
learned it from YouTube
Interesting.
lah. Yeah, from YouTube. It
Oh,
also
okay,
says
okay.
nice.
It's very interesting. I didn't really know this. Okay, okay. Thank you. All right, all
Anytime.
right. I see, I see. Okay. All right. I think I'm quite convinced already for 22. Um, yeah. I think so far I've done until 30, but I'll probably like do more so that yeah, lah, and if anything, I will ask you again.
Oh yeah, sure, sure.
So,
So
mm,
is there any questions you want to ask? Maybe one last question before we go.
yeah, sure. Comparison.
Oh yeah, 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 sure,
Comparison.
sure.
Yeah, 9.4. Okay. I'm kind of confused with. Wait, there are like a few, but I'm gonna pick one that I'm struggling the most.
All right.
Um, which is 36, I think. Yeah, 36. Mm.
30. Okay. Oh, all right.
Yeah, I tried doing. I mean, I tried doing limit LCT, but then
Okay.
no, no, I couldn't really do it. I don't know which is like which one I think I'm struggling with how to compare like which is the because in the examples they in the book a textbook and the
Yeah,
examples
yeah.
they will always have a known like bn would be something very simple that they can
All
compare
right.
it with but this
Mm.
one I don't know how to compare like I don't know which bn like what is the best bn to to test to
Mm-mm, mm-mm,
yeah use
mm-mm,
to
mm-mm.
mm,
Okay. So, you know what's funny? This one, you don't need any test. All you need is a theorem, which is the theorem for series.
oh
Now, yeah, one of the theorems are it states here. Let's say we have series A, which is equal to A, converges to A. Say we have series B converges to B. No, no, no. We don't need that. We don't need that information. All we need to know is one of the series converges and the other diverges. So let's say maybe
oh,
series A converges, con converges. B diverges, diverges. So what happens if both of the series plus or minus the other one? Which means that what happens if a converge series plus or minus with a diverge series? What happens? And I think if you go back to the previous theorems about this, the properties, you will be surprised that the resulting series will be diverges.
yeah, it is quite surprising.
Yeah. So this has to be
Mm,
converge, this has to be diverge. But if both diverges, then there's nothing to tell. Like you can't say that it is converging or diverging. You can't tell. But this only
oh,
works if one of them converges. Then the resulting series will
mm,
always be diverge. Lah.
I
Okay.
see. Uh-huh.
Now let's try and apply that fact that we have. So how do we apply it? Now, lucky for us, the numerator is addition between two terms, and our denominator has one term. So that implies that we can separate them, right?
Yes, yes. Mm-hmm.
So we are left with one over n to the power of n, and then the other one will be one over n squared, right?
Mm-hmm, mm-hmm.
Well,
Uh-huh.
this is a P series. It converge. But how about this series? If it can show that it diverges, then we are good to go. The whole thing diverges. But how do we show? And I take it back. Maybe we have to use a test. So which test is
Mm,
suitable? Hmm. Okay. So the thing is, we have to show this diverge. So let's try and find a series where makes it diverges. Hmm. How about 1 over n? The series, the harmonic series. One of the basic series we know it diverges. So let's try and apply for limit comparison, no, direct comparison test. Okay, so by comparing side by side, you could see that the left hand side will always be larger than the right hand side will always be larger than the left hand side. So, um, wait, if it's larger, right, then the test fails. Yeah, remember? If a diverge
oh,
series
okay.
always be larger, then it fails. So we can't use direct comparison test. Now, how about
Okay.
limit comparison test? All right, let's see what happens. So the limit n approaches to infinity for a over b, where a is the test series, b is a known series. And as you can see, our test series is 1 over n to the power of 2n. And our known series, our known series will be n, because divided by a reciprocal function will be a function.
Mm-hmm.
We're
Uh-huh.
left with limit n approaches to infinity 1 over 2 to the power of n, which is equal to 0. But we know it fails again. You know why?
Oh,
It's equal to
mm.
0, converge, but 1 over n diverges. So
Oh,
what is the
so
problem?
mm,
Okay, so both tests fails.
I
All right,
see.
both tests fails. Let me try. Okay, so but remember, this could converge, right? This can converge. So,
Uh-huh.
if it converges, then the addition of another converged series converges. The whole thing converges.
Mm-hmm.
Okay. All right. So let's try that. Maybe if you want to show it converges, then we have to compare with 1 over 2 to the power of n,
Oh,
because this
okay.
converge. You know why?
Mm-hmm.
Because it's a geometric series, a common ratio, but we have to make it as a geometric series form. So we have 1 over 2 to the power of n, and this converges by the geometric series of the common ratio less than 1.
Mm, mm,
So From here, alright then, let's try the direct comparison test again. Who knows, maybe it works. So side by side comparing, well, I can just write it down as 1 over 2 to the power of n, 1 over n to the power of n, and we know that n and 1. Well, this looks promising. So it'll always be larger than equal to. The left hand side will always be larger than equal to. Hmm.
Mm.
So we can build inequality. And you know why? Because here it satisfies the conditions for the direct comparison test. This converges as larger than equal to our test series, which is this one. So from the test, you could see that if this converges, uh, then this converges. Hmm.
Oh,
So this
mhm.
converge from the test states that this converge. Now, a converging series plus with another converging series means that the whole series converges. Then the answer will be therefore,
Oh, then the series converge lah.
yep.
Oh, mm,
So
mm,
one of the things that we could take from this question
mhm,
is that to to fail to to achieve success, you have to fail being a failure first. So yeah, the previous
mm,
ones we tried with this series and doesn't work twice. Limit comparison test doesn't work. Direct comparison doesn't work. So we have to find another way. Maybe you could compare a converge series, just 1 over 2 to the power of n, and it works.
mm,
Which means that it converge. Then it's a great news because a converging series plus with a converging series, the whole series converges.
mm. I see. So the BN too is like trial and error lah with your BN also in a way lah.
Yep, there is no other way. You have
Mm,
to try and error.
okay. Oh, I see, I see. Oh, so okay, I didn't know that you can do okay because like this one's new about the addition of convergent and convert another convergent series. Oh,
Yep.
and then to apply to this question, so it's like okay,
Yep.
it's a bit of what we learned in the past and what we learned with the LCT, DCT kind lah.
Yep.
I see. Yeah, okay. Alright, alright. Yeah,
Oh,
I think I'm good
it's fun.
for yeah. It's actually I can say actually I have more questions to ask, but ask later. So yeah.
Yeah, yeah, sure,
Mm,
sure, no
mm, mm.
problem. I believe
Then.
tomorrow you can like direct,
Mhm.
give me some questions personally. Yeah, I could do that.
Oh, okay, alright. Yeah. I'm sorry, yeah, today I was busy, so it's like
It's
didn't
okay.
have
I'm also
time.
busy today as well.
Yeah, okay, no worries.
All
Yeah,
right.
yeah.
So,
Yeah, so thank you, Aris, for
hey,
helping
anytime.
me.